Okay, welcoming people to the second live stream of today. We are talking about chemistry functionality for version 12.2. People might be noticing a theme that version 12.2 is approaching, and we're increasing the number of design review live streams. So many more to come, even another one today, I think. All right, let me go ahead and try and run this. Let's hope that works. It's grinding a lot. That's a lot. What's it doing? Is it going to hang?
It's mostly handshaking and getting the things.
Okay, great. Okay, molecule draw. What on earth is this?
Right, Many people want to sketch one, but Jason, you're much more expert than me.
So chemists, I mean, typically like to draw a molecule
rather
than
who made this? What is this?
This is mine. It needs a lot of work aesthetically. Let's see, the dynamics is not my forte, but it currently works. We need to get a lot of feedback before.
How does it work?
More time into it. Yeah.
No, that's not the right UX. I mean, that it's got to have some dragging thing go on, but that's interesting. Okay.
So then at this point, you could click redraw, the button on the bottom, and you'll see.
And it will turn it. Oh, that's cool. Okay, who's going to help with this UX? So that's the smile string that I just generated, right?
Right, and you can type into
that
smile
if
string.
I do this, what happens if I select that and I then do that?
That should, yeah,
make a double bond. Okay.
You can select an atom and then hover and then change an atom type.
No, I can't because I've got to preset. No, look. See that? How can I UX-wise go over here, right? See what I'm saying? If I pick phosphorus and then I click that atom, then great, I've got phosphorus there. See what I'm saying? Mm-hmm. So it's taken out. Do we have anybody from UX here? The best person to look at this would be Noah. I mean, this looks very promising, but I think the UX is very confusing. This is a say what you're going to do, then do it type UX, right? Which is kind of not what people are used to these days.
I mean, there are plenty of them out there, and I think it was mostly modeled after existing ones.
Okay. What are these? What's that? It doesn't have a mouse
zoom.
Over.
Yeah, I need
doesn't
to
have
give
a
it
mouse over.
Right, I need so that zoom in and zoom out.
That shouldn't be there. That should be somehow on the canvas. Do you understand what I'm saying?
Yes. Let me start my
note. And that's already a pattern that we have for things like dynamic geographics. Already has a plus minus zoom button that's visible in the canvas.
I will look at that and model it after that.
Okay. So I think here, I would say if you're really going to do this, specify it, then do it, you want this on the left-hand side. Do you understand what I'm saying?
Yeah.
But I don't know, because this seems like a modifier, and so really, is that really a thing?
Quintuple They're very uncommon.
They're more common in inorganic chemistry than organic chemistry, but they are quite frequent.
So for both the atom and the bond, I just don't know how to do this, but I think ideally you would have one button that shows the current atom type, the new atom type, and a click and hold would pull up the entire periodic table. Then you just reach over and select which one you want. And there's just one button for a bond, and you click and hold and it pulls up the list of all the types of bonds. I just don't know how to do that at the moment.
You don't know how to implement it, or you don't know how to do the UX for it?
I don't know how to implement
okay, but that's a different thing. Do you understand the UX that you want to achieve?
Yes.
Okay, I like that. Have you been working with somebody in the front end team to actually do this?
No.
Okay, so you need to do that. Lou or Kevin or somebody like that, okay? So tell them what you want to achieve and see if they can tell you how to achieve it.
Yeah.
Okay. So essentially what you're saying is you click something. Well, I don't know what I'm doing here. So now what on earth is that doing?
So you just added a disconnected atom.
Right, because I'm in the mode where I'm adding atoms. You know, look, Noah just spent like 6 months working on our drawing tools. Please talk to him.
Okay.
Okay. And if you need me to be in that meeting, I can be there. But you know, this looks, yeah, you should learn what he's done. Okay.
One meta question that we discussed is, should it bring up something new or should it be something in the notebook that stays there?
I don't know, and I don't know what's implementationally possible right now. I think it should do whatever, I don't know what create canvas does. It isn't even implemented. It's supposed to do, it should do the same thing that does. That is the drawing tools analog of this. Do you understand what I'm saying? Yeah. This needs to be integrated with drawing tools. Okay, you apparently haven't talked to anybody who's dealing with that. That's where it needs to go.
That's not quite true. Like this comes basically before the geometry was split off into the molecule and the geometry, and before we had many meetings active with Noah about it.
Okay, well, fine, good. I mean, this looks very close. It's just got, you know, details that are wrong, and which will make it much less usable. Yeah, I mean, it's just totally unclear what to do at this point here, right? That's just, it's completely unclear. You've set carbon as the default here for some random reason. See what I'm saying?
Yeah.
Yeah, but in Jason's defense, Stephen, carbon is what chemists typically draw with for the most part. So having that be the first choice is very reasonable.
Whatever, but I mean, it's the state of this is just utterly confusing. This is an afterthought. It's on the right. It's just, no, it's wrong.
Okay, we'll work with the front end team, come up with a better UX.
And Noah, because he's the one who's thought about drawing tools UX. Okay, and then I'd like to, I mean, this looks like very, very useful functionality and not far away from being really good. But like the drawing tools, which for 20 years have languished in the category of not quite there, this has the habit of, you know, this will do the same thing unless we get it right.
Okay.
So, okay.
So these don't have futurized doc pages yet, but I just wanted to verify that I can add these in.
Well, this is atom style. Necessary. Yeah, that seems reasonable. But I mean, this should work like edge style does in plots, right?
Yeah. So it should allow you to style specific atoms, and also
how does edge style work? Edge style basically tells you, in edge style, you give it a, well, this would be vertex style, right? What you would do is vertex style would let you give a list of rules of the form vertex goes to whatever. Okay, so that's exactly what
you don't mean plot, you mean graph plot.
I meant graph, actually.
Okay, good.
Yeah, right. This is exactly what that does, so that's good. So that's either a name of a vertex or it's a class of vertices here, right?
Yes.
What does that mean?
So I mean, so that's something that can be used right currently in like fine molecule substructure or molecule.
What does the hydrogen count mean?
I mean, so it just means to find a carbon or nitrogen with at least one hydrogen attached.
I don't understand this bug. This selection bug is still here. I've reported it like every day for the last 2 weeks.
Yeah, yeah, it's been around since we switched to 12.2. I feel like, but yeah.
Okay, that looks good. That atom style thing looks good.
Right, and then the one that I haven't even done yet, but let's see, allow the users.
That brace there is wrong, right? Oh no, that I see. I'm sorry, that's the outer brace. Yeah, right. Go ahead. Yes.
So the shape functions. So to allow users to really just put in any kind of arbitrary shape for an atom or for a bond. So we don't currently have any mechanism for putting it. It's common in these, when you write a paper or something, to put just a pH there to signify that there's a phenyl group. We don't currently support that in our data structure, but if the user wants to create that for a visualization, that's what the atom shape function would be used for.
But it's not just an atom.
So
I mean, it's not an atom shape. That's a whole. How do you specify that whole group being substituted that way?
So in that case, the user would just create a dummy atom and give it an atom shape function of pH.
But what if they actually want it to be an actual phenyl group, but they just want the phenyl group to be displayed in its aggregated form like this?
So that's a more complicated.
We are discussing this in a couple of weeks. Yeah,
because that's something which has come up also in System Modeler, right? In System Modeler, they have this notion of hierarchical structures. How do they handle it? Do you understand what I'm asking? Right. So in that case, you can have this can be an op amp or something. And that appears as a single blob at one level, and then you can click down and see it inside. So
right.
That seems to me to be the model that you want here, right? Because you might want to, in general, I don't know how hierarchical it gets in chemistry. How hierarchical does it get?
Well, so when we do, we're going to need to go to having a macromolecule data structure to connect between this work and what John is doing, and there having a hierarchical plotting function is going to be indispensable.
Okay.
Looking at things as ribbons versus scaling, zooming.
Yeah, I understand.
Out.
So we need a pattern then for dealing with something which is a higher level visualization, right? Which has aggregated certain things.
It's not just visualization. Like you also want, say, to prescribe molecular weights and other properties of the thing.
Okay, fine. So what you've got is a wrapper that represents. So this pH thing would be some kind of wrapper that says this is actually a pH, but inside is all this stuff.
Right. So that's come up in the meetings. People in the group have wanted some type of super atom, and so I was trying to slide this in just as a visualization. But if we want to do some type of super atom, then it's going to require more thought.
Yeah, I think it requires more thought. I mean,
go ahead. I like the hierarchical aspect as well, that we could nest it as deeply as we wanted to.
Right.
Yep.
Yeah. Really let's go that way, Jason.
I mean, and then whatever the superatom is, what would we call that thing? What would it be called in chemistry? It's not really a chemical group because that's something more specific. What is it?
A moiety.
Yeah.
Oh, gosh.
A moiety would be a proper term for it.
I think our group would be a perfectly fine one as well.
Yeah, but our group is from the organic side. The inorganic community uses ligands. Moiety is the neutral between the two communities.
Yeah.
Moiety is more general, so I would go with that.
Which one?
Moiety?
Moiety is
except nobody's ever heard of it.
Well, chemists have.
Chemists have. I still think our group is going to have. It's got a nice name, and all chemists would, even inorganic chemists, I think, would understand what it's supposed to do.
Archive might be strange if it's something in the middle that has multiple things going out, wouldn't it?
Yes. Usually our groups have single hapticity.
Like they're only at the end, but not in the middle.
Correct.
Yeah. Moiety's going to be better.
It's a really freaking weird word.
Yeah, agreed.
I thought it was too when I took organic chemistry, but it's been around for ages.
Yeah.
It's a term of art. It's a term of art.
I don't know.
Okay, I will tell you that if you look up moiety in a dictionary, the first things you see are anthropological terms about each of two parts into which a thing can be divided. Moiety in law. I have never heard of this in chemistry. Well, that has a...
So quite frankly, I think atom could be used for it. The symbol atom is near upon useless. I mean, it has one purpose, representing an atom inside a molecule or as a pattern. So it could
substituent. Is that a term?
That is a term.
Yeah. But again, it tends to imply just a single connection.
Right.
Okay. Well, I think moiety is too weird a word. Amusing, but weird.
Well, unfortunately, the whole field of chemistry disagrees.
It's more than 2 million Google Scholar hits.
Really? Well, okay,
Yep.
damn wrong. Someone on a live stream in Tar is suggesting superstructure. Yeah, various people here are commenting that ligands more common with polymers and R groups more common with organic. Superstructures are an equivalence class of many molecules that have identical function. Yeah, Pi is commenting that when you say R subgroup, it's like using the word X to represent a variable. The R is what you would put in as the thing in the diagram, typically, right?
Yep.
In the inorganic community, yes.
Right. Well, okay, so there's a naming question here, and I don't think atom is going to cut it. I think that's too confusing. To have an atom that's a whole amino acid or something, which is what you end up with.
Okay, I mean, so really though, I was
molecule part. No, that unfortunately that suggests like it's part extraction. Go ahead. What were you saying, Bob?
Well, just so with these molecules up above where they have a pH, I mean, those should exist. They should be in the all atom representation. When they're in the molecule, they should be expanded, and there should be a visualization option for contracting them and displaying them as pH or something.
Right, I agree.
Yeah, I don't. Let's see. So if we moving to a place where we represent entire substructures as symbolic pieces, there's a lot that would need to go into supporting
what I'm suggesting is that in your molecular structure, right, you have a wrapper around. I mean, what you've got right now is a list of atoms and bonds in here, right? So the issue is if you wrapped that, okay, there's a bit of a problem here, but the naive thing to do would be to wrap that list of atoms and bonds with some wrapper that means this is a chemical substructure thing, moiety, whatever you call it, right? But the problem with that is that it has bonds hanging out of it. So and it's not clear. Go ahead. Yeah.
Well, so let's see. So we have these things. We've discussed the idea of hyper edges, right? So we have these things, stereo groups, which is a collection of 5 atoms or a collection of 4 atoms, and we say specifically that they have such and such relationship in 3D space. Specifically with tetrahedral centers, we'll say that these 4 atoms are situated around this 5th atom in such a way that the signed volume, when taken in this order, is positive or negative. That I've been thinking and building the case slowly that that should extend to be a third argument where you have atoms, bonds, and then groups, which can be stereo groups, the ones we support, stereo groups that we don't currently support, which Bob has been interested in, among other people, types of stereochemistry that we don't currently support. And it could also include elided groups or something that we want to indicate that these atoms, which you find in list 1, which also have bonds that you found in list 2, they are a substructure, and we put them in this list of hyper edges, or whatever word we want to use to describe it.
But that's only one level deep. Then you couldn't actually nest that.
Yeah, which is right.
I don't know. This nesting sounds like a lot of work, and
well,
I don't know what
let's find out what System Modeler does and see how they handle it.
Right, because this is exactly, they have exactly the same issue. They have effectively bonds hanging out. In fact, even I think their representation is a so-called bond graph.
Yeah.
Right. So let's figure out.
I know
how that
several
works.
people in Jan's group, so let me talk with them.
Okay. Okay. Let's keep going here. But atom style and bond style both look fine. Somehow I have this view of, never mind. Okay. Simplifying the concept of using implicit hydrogens. It does or doesn't have the hydrogens in its internal representation. Yes, I agree with that statement.
Right. Right now, our data structure, we make use of a lot of cheminformatics tools. And I think that this may have overly influenced the data structure that we use. And so, so in a SMILES string, which comes from the world of cheminformatics, just C is methane.
Yeah, right.
But this is counterintuitive to our users, though, I think.
Right.
So what we would still interpret the SMILES string of C as methane and the SMILES string of O as oxygen or as water. But when you put that inside a list like this.
I agree. I think that's utterly confusing. It would just be an oxygen atom.
Yeah. And so then after this change, the functions add hydrogen and remove hydrogens would, instead of what they currently do, which is convert between implicit and explicit, they would convert between hydrogens and hairs. Unpaired electrons. Or
what exactly? When you remove the hydrogens, what's left over? What's left over is something which in the molecule representation is just a naked C, for example.
Right, and it would have...
with its... Go ahead.
If you ask how many unpaired electrons did that have, then the naked C would tell you it had 4.
How do you ask for the number of unpaired electrons?
I believe it's a molecule property, unpaired electron count.
Okay. Well, I agree. This makes more sense.
And so what this means is that users who create molecule expressions in 12.0 or 12.1 and then read them back in 12.2, if they did not call set options include hydrogens goes to true,
which they will not have done,
then the molecules, when read into 12.2, could be different.
Well, so let's understand how that works. So what's the case where it's different? Well, the case where it's different is this case here, right? Where somebody put that in. So if they had generated a molecule, let's say they generated, let's say that they put in methane as a molecule. So they said molecule okay, what is that? So that's fine. That's got explicit hydrogens in it.
Right.
Right?
Yep.
So if they created a molecule of methane and include hydrogens goes to false.
No, I understand. I understand that. What I'm trying to understand is if they did it from entities, they will have no problem, right?
True.
The case where they will have trouble is where, and I'm sure we've got examples of this kind, where somebody just did, table. Okay, so let me understand what will happen here. So if I say table C5, then, and I just say molecule of that, the question is, do I get pentane or whatever it is, or do I get garbage?
Well, there you get 5 disconnected methane molecules.
But that's not the...
And in the future, you'll get 5 disconnected carbon atoms.
How do I make that a bond?
Right. So then the second argument would be, bond / at, so I mean, you can...
Okay, so you're saying, I see, this is different from like string join of table C5, which would give the smile string, which will then, like as now as before, would generate something with added hydrogens, right?
Right. Although let's see, the expression there, the hydrogens are left implicit. They are not in it, and therein lies the trouble.
Oh, that's not going to work. That's not going to work. Okay. So what do you know? Okay, that's going to be a disaster. Okay, so let's figure out how we back out of this. Right, so let's look at the expressions you get from smile strings. Right, do you understand what I'm asking? I'm saying I think you'll be going to be able to have some clue from the fact that it's something that has all of this stuff filled in, all this bond information filled in. Aren't you going to be able to get different information here?
So in 12.2, where we would know, so in 12.2 we wouldn't, let's see, we would look at that and we would say this user clearly wanted to create a chain of 5 carbon atoms without hydrogens.
I understand. I'm asking you, given what you see here, right, is there at least a heuristic that would tell you, was this generated from a smile string? As opposed to, did somebody type this in? Do you understand what I'm asking?
So no, the expressions...
I understand that you can, in principle, get the same expression, right?
Right. I'm just saying that currently the code.
I understand. You can, in principle, type in the same expression. That's not the question I'm asking.
There's no history.
Go ahead. What?
There's no history, so you cannot know that it comes from smiles or something else.
Guys, how about some thinking here?
That's not what Stephen is asking.
Right. Thank you, Michael. Right.
I think the hint would be that as the expression that comes here is as ordered as possible.
Yes.
I think a human might do something slightly different from time to time.
Well, and among other things, this canonicalizes the fact that this has atom wrappers around the C's. Is that a hint? Or does that happen? In other words, a user who typed this in, if I typed in just CC like this, how does that canonicalize? Oh, it doesn't even have the bond information, but how does that canonicalize?
It does right. Put in the atom wrappers.
All right, okay. Okay, our goal is the following. For version 12.2, but not thereafter, to be able to put a warning that indicates that heuristically, this might be not what you think it is. So to speak.
I mean, heuristically, I would assume the vast majority of users will have all bonds saturated by hydrogen. So if we encounter in the new philosophy one that has unpaired one, that's probably the situation that's rare, and we should give the message.
That's what I suspect too.
And should that be a literal message or something by the predictive interface saying?
A message. In this version, a message. Okay, it just says assuming. So what is the form of this that you would get you're proposing to get in 12.2? This case, right? I enter this thing. What do I get out? What is the input form in that case?
Right.
So, you understand my question?
Yeah. So where you have just 5 disconnected vertices.
No. This smile string molecule of
string
5C.
I'm sorry. Yes.
Okay. What would I get out in that case?
Like what you got earlier if you had added the option.
Okay. So let me do that now. So this is now I would add the option include hydrogens arrow true. Correct?
Yes.
Okay, so one of the arguments that you guys gave me before was, oh, it's too big a data structure if you put all the hydrogens in, right? Where did that argument go?
So
we come back with the next point from Jason.
Yeah, the next point on down is that I also want to make the molecule an atomic, so that
No. I mean, so you can't do what I just did here with input form?
Well, you can always use input form, but it's not, it would be, let's see, an internal format that is easily recognized by the system as one that was created internally, and it's just faster to load.
So wait a minute. So you're proposing to make an incompatible change in this version, so that, and then you're going to make another incompatible change to no.
No. There's no second one.
Well, but the point is that if you were going to make this change, well, I see, because you still can read the thing in. All right. So the goal is,
basically, while everybody in this group who works with computers thought it was a good idea to not have hydrogen, it turns out for many chemists it's not the right idea.
Yes, but you want to basically do that implicitly by having your internal data structure be something different. Is that right?
Right.
Right. So the input form would recover the hydrogens, but the internal data structure would not have them in, or some other crazy thing with the internal data structure.
If you scroll down, it shows an example of what I would.
Yeah.
I love the fact. I mean,
so essentially, if you do a random graph or get a graph from some situation, some of the times when you look at its input form, it's what is it, a sparse array, and it's got the word automatic in there. It's clearly an internal format that is used internally. And so when
I'm not a big fan of having the input form molecule not actually recover the input form. I think that, recover an input form, I think that's an unfortunate feature of graph. But I think that what is stored does not necessarily have to be, input form can do work to get it into the format that it shows. Do you understand what I'm saying?
Right. I know. I've seen that done in the kernel.
Okay.
I'm not familiar.
Fine.
I'm not familiar.
I don't
with things
want them
done
to know about the implementation, right? We can clearly implement that.
Mm-hmm.
Right? We don't need to discuss it here.
But wait a minute. So you want to keep the old form even when written to a file? Because this is the scenario that Jason mostly tries to address, where he reads 1 million molecules from a file.
So it's always
if you read 1 million molecules from a file, you might as well have a binary format that it keeps them in.
So it's always bothered me that for tests, I would keep a list of 10,000 smile strings that I can pull up rather quickly. And it's faster to generate the molecules from those smile strings than it is to then reread in the input form.
Why don't you make the input form be the smile string then? Why are you making this weird thing here?
But it's even less readable by a human.
Then this is completely unreadable by a human. A smile string is at least obviously a molecule.
Right, I guess the smile string seemed to bridge too far to me, but...
Okay, look. Okay, you've got two different things going on here. First, you think, as I in fact argued, we can go back and that this, this removing hydrogens was kind of a hack, right? Turns out it is kind of a hack, so we can't do it, right? So now you're concerned that the data structure you get is too big and blobulous, right?
Yes.
So, okay, so let's think about this for a second. So, how would you get this explicit list out of a molecule, which is clearly a useful list to have? How would you get that list?
Well, so you can always call so say you have mol1, you can always call molecule of atom list of mol1, comma, bond list of mol1.
Okay, so that's the direct analog of vertex list and edge list for graphs, right?
Yes.
Okay.
So have to keep in mind that if the molecule has 3D coordinates, those have to be carried along as well. And we've been kind of ignoring that so far and just looking at atoms and bonds. And for me, when a molecule has coordinates, you've got to have all the hydrogens there as well. or if you're editing it and you remove one of the hydrogen atoms because you want to do something in its place, things have to work accordingly and not lose all the other coordinates.
No, but I mean, what you're saying is you want a blob here that represents the molecule, okay? Just like for a graph, we just have a blob that represents it. You're not expected to go inside. Just like for a graph, I mean, so here, right, this is the analog for graph of, if I just say random graph, okay, I've got a random graph. Now, obviously, it helps that it's just displaying as a graph. And I've got a question here. Why do we display this? I mean, I think doing this as a molecule like this is fine, but I'm wondering whether this should actually be made smaller and whether we should have a bigger picture here.
No, I mean, it definitely needs work. We have cases where the aspect ratio of the molecule itself is so far from 1 that the summary boxes look awful, in my opinion.
Okay, fine. But so what I would recommend here is reformatting this so that it has a much larger, so it's much more like a molecule plot. Just like in the case of graphs, we do still have graph plot, but mostly you just see the plot, right? Now, on the other hand, in the molecule case, you really do need to see the formula because otherwise you often can't tell what's going on. Am I making sense?
And so for that, I've always thought that the attached cell would be nice. When you click the molecule, the attached cell shows up down below.
No. But
I think, Anna, we had this discussion. I think not everybody agreed with you on this one.
Yeah, that's true. That's true.
Okay, so the atoms and bonds thing, I think that's superfluous, honestly, to show at the top level of the summary box. Do you agree? I think if we were going to do something like that, showing molecular weight seems more useful.
No, atoms and bonds are much easier to digest because it's integer information rather than real.
Okay.
Yeah, and the formula.
Right. So
you both wait. I'm trying to understand. So you find both of those things useful?
Yes.
Yes.
Yep.
Yeah, everybody else in the group besides myself likes the summary boxes. I still think they need to. It could be improved. That it could be like graph. It could display as the molecule plot, but annotate it somehow with.
Yeah, well, why not? Why not? I mean, but why not have something which is pretty much like this, like the molecule plot, but with a little legend down at the bottom that says the formula and says the atom count stuff.
So that would be right. So then it would be different than not strictly the same thing you get back from molecule plot. I mean,
no, it wouldn't be the same thing. Just like graph plot doesn't give you exactly the same thing as the default display form of graph. Graph plot gives you a graphics object. This thing here with the purple border is an actual graph object. Do you see what I'm saying?
Right, but I mean, I really liked it when we made the change recently where the default behavior from graph plot basically matched. Because a lot of people would say,
that's right. But let me point out, a graph plot is a graphics object. This is not a graphics object. Do you understand what I'm saying?
Absolutely.
Right, so graph plot of this has various different defaults. It probably has a different size. It is actually graphics. You see what I'm saying?
Yes.
And in the case of molecules, we could certainly have more of a difference. That is, it could have more annotation here because clearly the formula is useful. Right?
Yes.
Okay. By the way, when you generate this, I mean, this is clearly a shared data structure. So this is just pointer addition, adding to pointers, right? There's not a copy of the atom of H thing. I mean, that's just in terms of the way it's internally generated, that should be straightforward. But this is a big mess. This will add a lot more data, right?
Right. So the numerical form I was showing below is what essentially.
I know. I realize that. I understand that. I'm making a different point. Okay. I'm talking about this form here, right? And how you avoid this getting totally bloated, right?
Internally, not externally.
Well,
Externally, I don't see a real way to avoid the bloatedness.
No, I understand. If you're going to write this all out, well, there is one way, which is you could drop the bonds. These bonds going to the hydrogen atoms. I don't think you need to give them explicitly, do you? I guess you do. I guess you could say, if you had include hydrogen bonds or something in here as an option, then it would say, well, maybe you need to give them. I mean, if I don't know. You tell me. I mean, the bond list could give that, but it doesn't necessarily need to exist in this input form.
Right. So they don't. So whether or not if you look at the expression, whether or not you see the H's there should be immaterial. It's when you ask for the atom list or bond list, you can give the option include hydrogens, and
right.
You can get them or not.
Right. And so
abstract
then the default is for atom list, is the default to include the hydrogens or not?
It should be to include them.
Okay.
Yeah. If the users put them there,
no. The user hasn't put them there. The user has not put them there. The user gave a smile string. Do you include them by default or not? When you ask,
you include them.
Okay.
Because otherwise, if you don't have the hydrogen, you have a different
all right, fine.
species.
Fine. Okay.
I mean, one possibility would be maybe to make bond a more complicated thing that allows like multi-bonds, like multi-line. So it would serve at least to be able to save 60%.
I wouldn't bother. I wouldn't bother because I think the correct thing to do is to follow exactly the pattern that we have for graph. Okay, the pattern we have for graph.
So you said earlier you didn't like what graph does.
I'm changing my mind.
So if you make input form of this, you're fine with this.
Okay, let's look at this. Yeah, it's some garbage. Right.
But not totally incomprehensible. The user can take that sparse array and can understand that is the
nonsense. It's incomprehensible. It's incomprehensible.
When looking at it, yes, but a user who
no,
knows
it's incomprehensible. Doesn't matter. Nobody's going to use this. It doesn't matter what this is. I mean, personally, I'm not a big fan of the exact way this looks, but it doesn't matter. And you're not going to argue that this is a user, this is one of these things like it's a, if you buy a machine, it has no user serviceable parts, so to speak. And anybody who goes in and raw extracts part 3 of this graph object is simply going to end up in trouble because in version 14, it's going to change. Right, so I think it's okay. So what you're proposing is that molecule, like graph, is accessed. I mean, I don't know whether that's right.
So this would solve the earlier problem that we were talking about, right? So if
yes, of course it would.
If you get back something that is in the old canonical format and has dangling hairs all over the place, that tells you this.
Yes, that would do that. Yes, right. But there's a different point, which is one of the things that, for graph, for example, I had forgotten, I was reminded yesterday of the fact that you can give in a graph, when you say graph, you can give the first argument can be nodes, the second argument to be edges. I always specify a graph by giving just an edge list. Okay, so it is a pity pedagogically that there's no way to get out something where you can explicitly see this form, especially as Bob has pointed out, if you have stereochemistry data as a third argument. Right, to reconstitute a thing, you're then, I think the issue is right now we have molecule modify and things like that. Probably that should get more explicitly turned into things that are more like the graph theory operations. Am I making sense? Rather than just one grab bag of molecule modify. I'm concerned that there isn't a form. Okay, so look, what you guys basically are saying is you want to make a oh, that's cool. I don't think those are the right names, but anyway. Okay. So in any case, unless we're going to have a similar thing, which is like a hash or something, I mean, that's a question for the machine learning group, whether they want to have some similar generalized fingerprint function for other things. Okay, so back here. That's awful. That's just awful. That's just awful. You see, it's not the same thing with a graph, because for a graph, you just say edge list, and you just say graph of the edge list, and you can reconstruct it. Do you understand what I'm saying?
Right, and that's because the vertices are just plain vertices. They don't have a character to them like hydrogen, carbon, phosphorus. And we have to have that additional information.
Although I will point out, many people of our users make mistakes when they have just a graph that they create from an edge list, because they assume that the vertices are numeric,
exactly,
going from 1 up to n verts. But if they don't provide them in that order in the edge list, then there are cases of confusion among the users.
Sure. Right, but the difficulty here is this reconstitution thing. We got to find a better way to do this reconstitution thing.
I mean, so
for what purpose? I'm not quite sure what you mean by. If this thing anyway doesn't exist, why would you want to build it?
Well, you're saying, what I'm saying is, you want to do an operation on your molecule.
Yeah. You didn't look inside before, and you don't look inside after.
Yeah, except that for graphs, it's very common to pull out the edges, do something to them, and then, reconstitute the graph. You're claiming for molecules that is a less common thing to want to do. That you don't want to, for molecules, the moves you make have to be done by chemistry, at least in the current state of the world. And therefore...
Or by molecule modify, which has an extensive list of the moves you might want to do.
I know.
The drawing utility. So it's funny here that you're talking about pointers. You mentioned pointers above with the atom H, and what we're talking about here. I rather like them and wish that we had them more in the Wolfram language.
No. You don't even need them. You don't need them, because you've got the thing is implicitly turning itself into a pointer. What were you going to say?
Well, just let's see. So using undocumented things in the prototype build, I have it set up to where that the atoms that come back from atom list are actually pointers. That it says atom C is its input form, but you can ask it how many connections it has, and it knows. You can ask it what its parent molecule is.
I see.
But
let's have another discussion about this.
I can't convince anybody.
That's absolutely crazy.
Yeah.
No. Let's not go there, Jason. Please.
That's kind of spooky.
Okay. So one thing I would like to suggest is that we plan to take molecule modify, and we have I
mean, if you're going to say split it up, like break off some like atom add, atom delete functions, I love that idea.
Yeah, I think we should do that. Just like we have vertex add and so on in the case of graphs, I think that's what we should be looking at. Now, a good exercise. Okay, so I think my point of view is, go ahead and think about just making molecule be an opaque object, working like this. Okay, change its output form to be more, emphasizing the image. Makes sense?
Yes.
And I think I'm okay with that. Fine, try it. See what you can do. And as you say, we're solving the problem of, if you see a molecule in explicit molecule form, not in this digested form, then that is a clue that was a include hydrogens true default case. Right?
Yep.
Yes. And I was planning to put out a backlit update so that pre-12.0 and 12.1 could ingest the new molecules and convert them to the...
That would be good. I think you should have something in here that is essentially versioning information, even if it's implicit somehow. I don't quite know how to do that. I mean, you could have a method option here or something.
I mean, data set, mesh, region, they all have such stuff inside.
Yeah. What about the meta information element, Jason?
I tend to think of that as something the user
Right.
puts there.
We don't want to mess with that. Whatever mesh region and all those things do, you should copy that.
Okay.
Right?
Yeah.
So that we have versioning information, so we don't have this problem again. There's really nice stuff here, by the way.
Thank you.
It's really very impressive. So here's a test as far as I'm concerned, okay? So, you know, I've been doing all this stuff with random picture. Let's bring up a random picture. Oh, that's a random picture. That's the theorem network of Euclid. But that's not the most interesting thing. The most interesting thing is that doing proofs is like taking an expression and making progressive modifications to it. It's like chemistry. In other words, your sequence of, you know, your way of doing a sequence of essentially, you know, molecule modifies, you know, which are sort of junior versions of chemical reactions, is extremely similar to what's happening inside these multi-way systems, which is extremely similar to what's happening inside fine equational proof. Is this making any sense to anybody?
Does to me.
Yes.
Okay. So
I'm a little bit less convinced, because I think the one difference is that in the proof case, you have, say, a set of axioms or things that you apply, and for them there isn't a conservation law. But here, there are conservation laws which you kind of break at every point.
No, you can spray hydrogen gas onto your thing.
But like adding a hydrogen needs a hydrogen from somewhere where an axiom comes for free.
Actually, Michael, okay, so here's the thing. I have been actually quite deeply confused about the difference between equations and transformations and axioms and so on. There are actually several different ways to do this in math. And they all have nice correspondences. I don't think this is a huge problem. I think that the question of whether you in some, but the basic idea is, you know, what you've eventually got is something where you can imagine, okay, in one of these, I mean, in your average, where is it? Let me pull one up. Hold on. Let me pull one up here. You know, some random thing like this. Okay, so we think of this, if we imagine this as a bunch of potential chemical products. So this is, each arrow here represents some molecule modify that can be done, right?
Not really, because there is basically, for the molecule modify case, there's an implicit error where you either put something in or out. It's not just you take one and rewire it.
No, but look, the result of molecule modify is you take one molecule here, okay? And here we've got, let's take this example here. Okay, we've taken one molecule and we've got out a different molecule.
Yeah.
Okay, so this operation here is like one of these arrows. And this molecule here, that's this molecule, this one here is this molecule, let's say.
In this case, yes, but if you would have added an atom that wasn't there before, I feel like you have done something different.
Well, this was adding a bond that wasn't there before.
No, you somewhere got the atom itself that you added.
No, I understand. You're saying there's a physicality
Yes.
of atom counting
Yes.
that we're not necessarily taking account of here, although we certainly, yes, what's happening in this picture is these are unary operations. This is, you take this thing, you give an output, right?
Right,
You're
exactly.
You're saying that in another case, you've got another thing floating around here and you combine it with this. Okay.
Basically, so X's in Feynman diagrams.
Yes. You mean potentials or something in a Feynman diagram?
Which allow me to break conservation laws like momentum.
Yes. Okay. So, Michael, here's the point. If you look at find equational proof, it has the same thing going on. It has, if you look at the graph that it makes, it is bringing in another piece. It is essentially combining. What it's doing is it's applying one. Okay, so this is, it's quite confusing. I'm glad you're confused because I was very confused for about 2 weeks about this. Yeah. Okay, I mean, the difference is if these things had that there are 3 different forms. I'm about to write something about this, and then we'll all perhaps be less confused. There are, one thing is you take that this axiom. Okay, let's say this thing had an equal sign in it. Okay, that was an assertion that had an equal sign in. Then this edge is itself just like an assertion with the equal sign in. Okay. Now, a different way of thinking about it is that you can, but basically the point is that there's ways that there are different representations of this, some in which you are taking 2 theorems, you're taking one theorem and you're applying another theorem to that theorem to get a third theorem. That's what you do in implication, right?
Yeah.
A implies B, right? And that implicational form, I suspect, is more similar to you wheel in another set of atoms and combine them.
Okay, let me rephrase my thing. Like if I have a set of axioms or the string rewriting, I can generate infinite many different things by never needing something new. You can't generate infinitely new molecules if you don't also supply infinitely.
I understand. It's a question of whether you have a closed system or an open system.
Exactly.
I mean, but I think that that there are plenty of cases in chemistry where what you're interested in, some synthesis thing, is an open system, if I'm not mistaken. That's
right. That's right. Yes. For synthesis planning, it does not have to be closed. If we were trying to model something that was happening in a laboratory and we had, so many grams of this and so many grams of that to start with, and when we finish, we've got to have so many plus so many grams of something or some combination of things at the end, because it's a closed system.
Right. Okay. So yeah. Right.
So this theory here can certainly be open. The multi-way system.
Right. So okay. So then. Okay, so here's what the reason I'm bringing this up, okay, is because I want the design to be such that this would all just fit beautifully together, right? Because so one thing I realized, which I was super embarrassed to have not realized before, is that there is a really simple function, which I'm going to call find replace path, that given a set of rules, will just find the sequence of rules that you need to apply to get, for example, from AB to AAA. Right, so you can either generate the graph explicitly and then say find shortest path, right? Or you can simply say, if I were to pull this in, hold on 1 second here. Okay, this is find string replace path. Okay, so find string replace path would say this. In here, right, I would just say take those rules, and it's essentially virtually generating a graph. So if I say find, and this is, you're going to see why this is relevant in a moment. Okay, find string replace path of this. Let's say we go from AB to, I don't know, to ABA. Okay, so that's the path. So that is a virtually generated path, right? I could have explicitly generated the whole graph and then done a find shortest path to get that path, but instead, that's equivalent to saying find shortest. But you all understand this, right? Yes, find shortest path.
Yeah. What does it do if you give it one it can never reach? It hangs forever.
Find replace path. Yeah, it has limits here that are called max steps, max items, time constraint.
Okay.
Now, we actually have a new function called find counterexample find equational counterexample, which can prove that it can't be got to.
I saw this in the WFR today.
Right. Okay, so here, but the kind of the lame version of it is, okay, so there we go. All right, so now, and this is very similar, but not quite the same as find equational proof. And this isn't quite working. This isn't quite the same, right? So if I were to say find equational proof of AB equals ABA, I don't know if this will work yet. Let's take a look. Notice the unfortunate different argument order here because the axioms go second in find equational proof. Yeah, it doesn't, oh, shoot. Oh, yeah, because this is all screwed up. Yes, this doesn't work yet. But then this will generate a proof, right, which has a slightly different format than these things. But that proof, actually what that proof is showing is it shows the path, basically, and then it shows stubs of the path. So if I say, this isn't as irrelevant as you think it is, by the way. There's a whole discussion. Oh, God, why is this still broken? This is another thing that's still broken.
Bob, doesn't this look like retrosynthetic analysis?
Whether it's retro or not, it would be applicable, yes. But we're generally doing the forward direction here.
Yeah.
Retrosynthesis is
Backwards.
generally bigger steps to go backwards to find your general route.
Your starting materials. You start with the product and you go to the materials.
Right. So that is given this string, you want to know what is a path from the root to that string. So that, by the way, is, again, unfortunately, and Michael, I was so confused about this. I think I have finally unscrambled my confusion, but I won't know that until I've written about it. In some cases, you start from true and you are deriving all true statements. Okay?
Right.
And that's the analog of what you say is, how do I get to this thing here? Oh, I need to apply these axioms, heat it, shake it, whatever else. Oh, gosh. What is the command key? I never use the command key to
What, to complete it? Command-Shift-K. Or to a template.
You know what this is doing. When I did what I thought would do this on my keyboard, it caused my display to go blank. That's not what I wanted. I just want the, oh gosh. This is so frustrating. It's amazing how much one starts relying on these little user interface elements. Okay, so what I wanted to show you was, take a random proof graph here. Okay. Okay, so this, rather confusingly, is similar to, but not quite the same. So this essentially has one path. It should have one path that isn't dotted lines. So those are the axioms at the top. These things here, there should be, I'm now very confused about how this is working. Yeah, I think here you go. Here's the solid line that goes from the hypothesis down to the conclusion, right? And all the other stuff here is essentially prepping lemmas to use. Okay, so those are, what is the analog of a lemma in chemistry? So, it's a partial thing that you prepare that is a thing that will be fed in to put into the synthesis. So it's a
right.
A byproduct.
Yeah, but it's the inverse of a byproduct. It's what you're doing. It's not the byproduct would be something that comes out. It's something you prepare where you say, make this thing and then put it, go ahead.
I was going to say it could be thought of as state variable conditions, so temperature, pressure. It could be thought of as the solvent, the aqueous, the whatever environment they're in, gas phase.
It's more than that. It's more than that. You're building building blocks, basically. You're making a number of building blocks and then gluing them together in a particular sequence.
Right.
And do you do that
Intermediates.
commonly in chemical synthesis?
Yes.
Yes, yes.
Yes.
What's it
all
called
the
when
time.
you do that?
You assemble from intermediates, the bigger
Okay.
stuff, and then
Y- Yeah.
bigger things. Bring them together to make even bigger things.
Yeah.
Okay.
Intermediates is another term, or building blocks. Those are the two common terms.
Okay. All right. Okay. So then what this is saying is, so a lemma is one of these building blocks, basically, that you're then going to apply to get whatever you get here. Okay. So what I'm asking is, what I'd like to see, and maybe, I mean, is, ultimately what you want is this thing here. Well, actually, this is not a good example. This is, sorry, what am I asking for?
I think the situation is more complicated, because a variation of what I said earlier, like even with the building blocks, you don't make the raw building blocks with a couple of open bonds. You say have two molecules and then put them together and split a little bit up. So I think it's much more this open system paradigm where things come in all the time and go all the time.
Let me show you something. Find replace path. Okay, so let me show you this. Okay, so that's showing you essentially what you do at each step, right? That's the instructions for the synthesis, if that makes sense. Although this isn't showing you, it's not necessarily showing you where you apply those rules at each step, right? It's saying this is the rule at each step, but there could be multiple applications of a rule at a given step. And this is simply one of the paths. Okay, so you need to see the whole thing here. You need to have, there's a full representation that gives you the location at which this application is made, which is very similar to this. In fact, if we do this with official multi-way system, it will give you that information. So in other words, it's going to be something essentially identical to this. It's going to say, apply this substitution at this place, replace atom. Which atom are you replacing? Or, I mean, well, in this case, you're just replacing a single atom, but I assume you can glue in a particular place. You remove an atom and you add some ligandy thing on instead, right?
Yeah, in the regular organic synthesis world, the reagents would actually be doing that when you're coupling two intermediates together, or two building blocks, for example, with an ester linkage. You end up removing a molecule of water in the process, an OH from one side and an H from the other.
Okay, so let me ask this question. If I were to, if you have one of these all possible syntheses, does that get considered in chemistry? I mean, that must happen. If you just, take a bunch of molecules and you've got various things that are going on with them, if you just got a pot of stuff.
Yeah, those are called chemical rearrangements. I've been trying to study that a little bit since the summer school, but haven't gotten very far.
Yeah, and there's field called combinatorial chemistry where it's kind of like that. You mix a bunch of stuff, try to take the products and see what those products do.
Right. Although I thought combinatorial chemistry was much more of a something where you have a library and you're trying to do.
Right. It's more controlled, and you end up with many different things in many different pots.
So let me ask a naive question. If I'm, like oil or something, or when you have, I mean, I know so little chemistry, but I mean, when you have one of these things, you're just mixing together carbon and hydrogen, and you heat it up in some way, and various different lengths of polymers form, and so on. How do people think about that? How do people, you're just taking this random collection of things, and you're applying an operation, and you get a diversity, of different, for example, lengths of polymers, amounts of branching, those kinds of things. What is that?
It's a one pot something, but I'm not sure what you would call it.
Yeah, black tar.
I was just going to say it was the first year experiment that didn't go right.
Yeah, I mean, it's like not Urey Bradley, but the
Urey Miller experiment.
Yes, the Urey Miller experiment.
Yes.
Yeah.
Right. But I mean, I think okay. But so one pot synthesis is the general term for those kinds of things. Is that right?
Yeah,
Yes.
and hopefully you have a major product and not a giant gamish.
Yeah, we try to avoid complex mixtures as much as possible. We want large yields.
Right.
Yeah.
In other words, you want to follow a particular path in the synthesis thing.
Yeah.
Yeah.
Right. But so in see, the reason I'm okay. The thing is, we're going to have a really pretty nice set of essentially theorem-proving capabilities that, I mean, I understand that actual chemical synthesis has more complicated issues. It has all kinds of reaction rates and all kinds of things like this. But I'm just trying to understand, given that we've got a pattern for designing these kinds of things where there are many possible changes that can be made type thing, I'm just trying to understand. Actually, it occurs to me that we should have, I'm sorry, I'm just thinking about, we don't really have a graph modify function. The only thing we have is the whole, Wolfram model, hypergraph transformation stuff, which is pretty general. But it only, yes. Anyway, I'm sorry, I'm thinking out loud here, and we should wrap up in a minute. Go ahead.
After all this, I mean, the next step is to look at a chemical reaction as a data structure where you have a full atom mapping between reactants and products, and let's see. I mean, so before I arrived here, one of the people who was working at Alpha for a time, he was looking at this this paper about chematica, which is touching a lot of the points that you are where you have this this collection of graph transformations, and it was really trying to predict one pot synthesis routes, and we're developing the tools that we can look back at
Okay, but so one of the things that's an interesting issue is, like, for example, one thing we don't typically have in the language is we have something where you say, make a transformation to this expression. Okay, fine. The transformation, you say replace. The transformation is applied somewhere in that expression. If we ask the question, where did that transformation get applied? We don't have a particularly good way to represent that. See what I'm saying? So in other words, in these strings, I'm just saying, I'm using these rules, but I'm not saying which A, well, there probably weren't very many A's here, but which A was that string, which of the two A's did I apply that transformation to? See what I'm saying? And you're going to need that for the chemistry case.
Right. So the ideally, so we'll be able to deal with partially mapped chemical reactions, but in the ideal case, we'll have a full atom mapping, and you'll have cases where there are multiple matches, and so so that's when you apply that reaction to a list of chemicals, you would then get back a list of lists.
Right, exactly. But so, I mean, my point is, I don't even know, in chemical synthesis, right, it must be a problem if you have two such and such groups and you do a reaction that applies itself to a such and such group, you're going to get, both of them.
Both will react unless you've protected one specifically,
Yes.
and you can
Yes.
do that. That's an art in itself of different protecting groups being used appropriately to control your synthesis in the end. Yes.
But this gets back to those pre-building blocks. You would take your molecule, protect, i.e. turn off one of the groups that you don't want to react, that you have multiple of, and then you do the reaction that you want to change the thing of interest, and then you go back and unprotect the thing that you wanted to make sure it didn't change.
Right,
Yes.
and because the reaction that does the protection is very specific, it can distinguish the two groups that are there, in the original structure.
Right. So what you're saying is, what you're trying to do is, your goal is to have, a single path here, and which, in which everything, in which the path weight is basically 1 on that path and 0 on all other paths, to maximize the yield.
Ideally.
A failure.
Yeah,
right.
Ideally.
The yield is going to be the path weight of the path that leads you to the product you want.
Yes.
Right.
And so okay, so then a protecting group in the multi-way graph is something which basically, I hate to make these analogies, but it's the analog of a space-like singularity. I mean, it's a thing for which something has to be set up so that it cannot have rules applied to it. Yeah, okay.
Yeah, you're basically taking one of those B's and turning it into a C temporarily, and then you restore it back to its B character afterwards.
Yeah, you give it a distinguishing feature so it doesn't get touched by
I understand. But one of the things that you're doing in chemical synthesis, which is a little different from what you're doing here, is here you have a set of rules and you just say go, whereas the difference in chemistry is you say, for a while I'm going to heat it, then I'm going to cool it, then I'm going to do this, then I'm going to do that. So the chemistry has sort of different rules at different stages, so to speak. Yeah, we don't get rules,
but there's different. Yeah, there's different rules only determine which rule to apply. You just have a large set of rules, a much larger.
Yes, I understand. I mean, so is it true? I mean, the number of steps, it's like 30 steps or something, is there's kind of the limit of current synthesis technology? Is that about right? Is it more than that?
For some things, it's certainly more than that. There are protein synthesizers, nucleotide synthesizers that can go many, many more steps than that in good yield, but it's a very restricted set of chemistry. And
how many more steps, and in what case? In what kind of case?
They can put together hundreds of amino acids to make a protein.
And then there's also and then there's also the issue of what you call a convergent synthesis versus a linear synthesis. Usually, with the convergent synthesis, you can manage more steps because you're slowly building bigger things and then combining big things into even bigger things.
Right. Yeah.
Okay. So for example, if you're doing an oligonucleotide or something, if you're creating one of those, you're saying that that's like a synthesis reaction, where that's like synthesis, but you're going and chugging along and adding base pairs or something, adding amino acids or whatever. Is that right? I mean, is that what you mean by doing? That's the case where you think of, like, when you're creating some heteropolymer type thing, then you're able to do. But are there other cases where you're able to do a lot more?
For practical reasons, in reasonable yields, it's probably on the order of 20 or 30 total reactions, is what you typically see reported in the synthetic chemistry literature, at least organic. For some arbitrary natural product or something like that, that's not a polymer.
Okay, fair enough. All right, anyway, look, this is all irrelevant, but I just wanted to make this point because it would be nice to have some sort of uniformity to our way of doing, string replacements, molecule modifies, graph replacements, et cetera, et cetera, et cetera. And I also feel like what I really realized is that this replace path mechanism, logic programming is sort of a story of replace path, find replace path. That is, it's what sequence of moves do you have to make to get from here to there, and so on.
Mm-hmm.
And all of the various, and actually we have pretty efficient stuff for doing that. And I had thought we needed some specialized logic programming capability. We really don't. This is a clean way to present it, and I think potentially relevant for the chemistry thing.
Yeah.
Okay, comment on our live stream. Use pattern rule matching for rule selection. The pattern is a set of functional groups present in the reaction mixture. Right. Yes, the pattern is analog to functional group. Is that right? I mean, that's something where you can substitute in something else in that position.
Yeah.
Yeah.
Yes.
Well, very interesting. Okay.
Stephen, have the multi-way tools progressed to working on graphs yet in a general way?
Absolutely.
Yes.
Wait a minute. So the multi-way, yes, absolutely. You can apply them to hypergraphs.
Bob, remember the paper I sent around a while ago?
Yeah. Yeah, I've been working on a similar one.
Yeah, the one where they treat reactions as graph rewriting rules.
Right. Yeah, but so far, the last I worked with the multi-way stuff, it's on a hypergraph and not a graph with undirected edges. Or excuse me, not a hypergraph. It's a directed graph. And I finessed
that's
that.
a good point. Yes. That's a good point. We should make multi-way graph work, multi-way system work with ordinary graph objects. I agree. That would be. I mean, it's not difficult to do, but it's right now. But it's I mean, we had done one meeting on how to make multi-way graph multi-way system mainstream in the system, and I think we need to do another one. It's a fairly complicated function. But it's amazing how unified all of these different issues are. Okay, I'm just, I mean, and what, is there any meta statement when you're asking about chemical synthesis, so I mean, the reason I'm asking this, I've been working on this mathematics stuff where what one is trying to do is to make general statements about the structure of these multi-way systems and the possible proofs you can get and so on. What general statements are there about these kind of reaction pathway things? Are there any general statements in chemistry that people make? I mean, other than we want to get a particular path because that's the thing that gets us decent yield. Is there any? I mean, like for example, I guess people don't deal with that. In chemistry, like in programming, you don't want the ambiguity of getting lots of different things. You want a single path.
Yes.
Generally, that's right. Yeah.
That's correct.
But we do sort of abstract the edges in the sense that we have families of reactions that we know if your molecule has a particular shape or functional group, then we can talk about whole classes of reactions. So I don't know if that's quite what you're thinking about.
Maybe it's not quite the same thing, but I think, I mean, generally, look, in programming, this is like a representation of an asynchronous parallel programming type thing, and people find it very hard to think about this. And people generally, in writing code, try to reduce it to a single path. My guess is that, I mean, and like in chemistry, in a distributed computing system, you have no guarantee what's going to happen when. In other words, you can't.
Yes.
It's all asynchronous. So and you have to. What is the avoidance of a race condition in chemistry? That's your protecting group thing. You're protecting that avoids knowing which is going to happen in which order, avoiding the ambiguity of different ordering of different things happening. I suspect your protecting group thing is exactly analogous to something like one of these locks. That's like a lock in distributed computing.
Yeah, a lock is a good analogy for a protecting group. Yes.
Yep. One thing I'd like to say about this multi-way system, though, if you step back and look at something like biosynthesis of terpenoids, you start out with something very simple at the top, like farnesol, and you can produce at the bottom lots and lots of different sesquiterpenes. Not that a single organism produces them all, but if you look at all the different pathways of related organisms.
Well, that sounds interesting. What is that? What is that? Tell me what that is. I don't know how to spell those words. Biosynthesis, I can spell that. Of what?
Okay. Starting of sesquiterpenes, 15 carbon natural products made up of 3 isoprene units. And you start with farnesol or farnesyl pyrophosphate, which is mostly linear. It's got 3 extra methyl groups on it.
Are these the pheromone-like things that are used by various animals? Or is that
the pheromones are some things that are produced, yes, but they're monoterpenes, flavorings, and fragrances, menthol, camphor, and things like that. And in sesquiterpenes, a lot of them are antibiotics and sorts of things. They're produced by fungi and plants, and it's all secondary metabolism. and they're generally related to protecting the organism from predation by other organisms.
Yeah, allelopathic chemicals, sometimes called.
Yeah.
But so what you're saying here is when you do biosynthesis of these things, that I mean, is there some giant pathway giant sort of multi-way graph that people
right
make?
and some organisms follow some part of the pathway because of the enzymes that they have, and other organisms have a slightly different pathway because of their enzymes, and a lot of this has been worked out. You can actually see some of the evolutionary relationships of a collection of organisms that have
That's cool.
related compounds. Yeah, I looked at a lot of this stuff for my doctoral work, and hoping that I can
send me a link to a paper about this. This seems quite interesting. I mean,
okay, I'll dig some stuff up and send it to you.
Right, but I mean, so in principle, one could end up with a picture like this where every node is a molecule.
Yes.
And
yes.
Okay. Well, that'll be interesting. Okay, all right. We should go to different meetings here, but all right. So I think I mean, this chemistry stuff we're going to need to meet again, but it's looking good, and I think we have a direction here. All right.
Thank you.
Thanks, everybody.
Thank
Thanks,
you.
people on live
Thank you.
stream.
Okay, thank you.